Have you ever been right in the middle of something important online, maybe, I don't know, booking that holiday or paying a bill, and boom, suddenly the app just freezes up? Or you get that really unhelpful error message and everything just grinds to a halt. It's incredibly frustrating, isn't it? Well, today we're going to take a deep dive into something pretty fascinating: how modern applications, specifically using Spring Boot, are actually built to handle exactly those kinds of problems. We're exploring resilience and fault tolerance. Basically, how apps keep running smoothly even when things go sideways. Our guide for this is a really clear, beginner friendly summary. It breaks down these honestly quite complex ideas without getting you totally bogged down in code. It helps you understand the what, the why, and the how of building really solid apps. So our mission today: equip you with the key nuggets of knowledge so you can quickly grasp how these applications manage to stay reliable and, user-friendly even when they're under stress. Okay, so let's start right there. When we're talking about software, what exactly is resilience?
Right. So resilience at its core is really about an application's ability to keep doing its job, to keep working smoothly, even when things inevitably go wrong behind the scenes. Think of it maybe like a car that has a spare tire. If you
Hmm.
get a flat, you don't just abandon the car,
Right,
right?
go fix it. You keep going.
Exactly. You put on the spare and you continue your journey. The car itself hasn't failed fundamentally. It handled the specific problem, the flat tire. So in software terms, this means your app stays available, it stays responsive, provides a good experience, even if, say, one of its servers crashes, or maybe a database it needs goes offline for a bit, or some external service it talks to suddenly gets really slow. The main goal is keeping it available and responsive for the user.
That car analogy is great. It really clarifies it. Okay, so where does fault tolerance fit into that picture then? Is it something different or more like a part of resilience?
Oh, it's definitely part of it. I'd say fault tolerance is a really key piece of achieving resilience. If resilience is the overall goal, the car finishing its journey, fault tolerance is more about these specific mechanisms for handling those individual bumps in the road, those faults. It's about designing the application to anticipate certain kinds of failures and to manage them without, completely falling over. I like the analogy of a professional chef in a busy kitchen. If they suddenly run out of, say, lemons mid-service, a fault-tolerant chef doesn't just stop everything.
Yeah, dinner service doesn't just stop.
Exactly. They'll adapt. They might find a substitute, maybe use lime, or adjust the dish slightly, or perhaps even suggest an alternative menu item. They tolerate the fault, the missing ingredient, and work around it. In software, this stops those small issues, like a slow database query, from cascading into a massive problem, like the entire website going down.
I love that. The chef keeps the kitchen running, finds a workaround. Okay, so putting resilience and fault tolerance together, what does this mean for you listening, whether you're building apps or just using them every single day? Why does this really matter?
Oh, it matters a huge amount, especially if you're just getting started with development. It's fundamental. For the user, it simply means fewer of those frustrating error screens, fewer freezes, just a smoother, more reliable experience overall. From a developer's perspective, it's about building applications that don't constantly wake you up at 3 a.m. with alerts.
Yeah, nobody wants that.
Nobody wants that. So these concepts, they ensure apps keep running despite unexpected hiccups, server crashes, network glitches, you name it. They help guarantee a good user experience by minimizing those errors and delays. And for businesses, well, it's crucial for protecting their reputation. Imagine an online bank or a big e-commerce site just being down for hours. That's bad news.
Really bad.
And beyond that, it actually makes the applications easier to manage because a lot of the error handling becomes automatic. You're not scrambling to do manual fixes all the time. Plus, believe it or not, it can save costs.
Uh-huh.
Less downtime, less manual intervention, maybe less need for massively over-provisioned hardware, just in case. Ultimately, it's all about building Spring Boot apps that are, well, tough, reliable, and actually pleasant to use.
Okay, so we've got the what's and the why. Resilience, fault tolerance, super important. But the big question is how? How do Spring Boot applications actually pull this off? What are the tools in the box? What are the mechanisms?
Right, this is where it gets practical. And the good news is Spring Boot and its ecosystem offer some really powerful, but often surprisingly straightforward ways to implement this stuff.
Yeah.
Let's break down the main techniques. Okay, first up, probably the most famous one, circuit breakers.
Okay.
Think of these like an electrical circuit breaker in your house. If an appliance starts drawing too much current and risks causing a fire, the breaker trips, cutting off power to that circuit, right?
Yep, protects the rest of the house.
Exactly. In software, a circuit breaker monitors calls to an external service, maybe that payment API we mentioned, or a stock quote service. If that service starts failing repeatedly or becomes really slow, the circuit breaker opens. This immediately stops your application from sending any more requests to that struggling service for a little while.
Ah, so it prevents your app from just banging its head against a brick wall, basically, and probably slowing itself down in the process.
Precisely. Instead of your app grinding to a halt waiting for responses that never come or getting overwhelmed by cascading failures, the circuit breaker trips. But crucially, it doesn't just stay open forever. After a set timeout, it might go into a half-open state. It lets just one test request through. If that succeeds, great. The service seems to be back online, so the breaker closes and lets traffic flow normally again.
Clever.
If that test request fails, though, it stays open, continuing to protect your application. It's about failing fast and giving the downstream service time to recover.
So it isolates the problem and checks if it's fixed later. That's really smart. Okay, what else is in the toolbox?
Well, often working alongside circuit breakers, you have retries. This one's pretty intuitive. Sometimes a failure isn't catastrophic, it's just a temporary glitch, a brief network flicker, a database connection timing out for a split second.
It happens all the time.
It does. So with retries configured, your application will automatically try that failed operation again, maybe once or twice, perhaps with a short pause in between. It's like redialing a number if you get a busy signal the first time. You hope it was just temporary.
Right.
This handles those transient errors really gracefully, often without the user even noticing anything went wrong. It just succeeds on the second try.
Yeah, I can see how that would smooth over a lot of minor bumps. So, okay, you retry, it still fails, or maybe the circuit breaker is open. What then? Just show an error.
Well, ideally not. That's where fallbacks come in. A fallback is your application's plan B. If the primary way of doing something fails, like fetching live product prices from a database and maybe retries didn't help, the fallback provides an alternative response.
Okay, like what kind of alternative?
It could be anything, really.
Yeah.
Maybe it serves slightly older prices from a cache. Maybe it shows a default message like, price information currently unavailable, please check back soon. Or perhaps it uses a simpler, less resource-intensive version of the operation. Think back to the chef analogy. If the specific fancy dish is impossible, maybe they offer a reliable pre-made soup or sandwich instead. The goal is to still provide some value or reasonable response to the user, rather than just crashing or showing a raw error.
Got it. Keep the user journey moving, even if it's slightly degraded. Makes sense. What else?
Then there are timeouts. This is super important for responsiveness. You basically set a maximum time limit for how long your application is willing to wait for an operation to complete. This could be waiting for a database query or waiting for a response from that external API.
Yep.
If the response doesn't come back within that specified time, say 2 seconds or 5 seconds, your application just gives up on that specific request and moves on.
Stops it from just hanging there forever.
Exactly. It prevents one slow component from dragging down the entire application's performance or causing threads to pile up waiting. It's like setting a timer. If the pizza isn't here in 30 minutes, you stop waiting and figure something else out.
Yeah.
It enforces a boundary on waiting time.
Yeah, I can definitely see how crucial that is. A hanging app is a dead app, basically.
Pretty much. And finally, let's talk about caching. This is a huge enabler for resilience, especially for fallbacks. Caching means storing frequently accessed data like user profiles, product catalogs, configuration settings in a really fast, temporary storage, often in memory, using tools like Redis or cache. So if your primary database is slow or temporarily unavailable, your application can often still serve the request using the data it has stored in the cache. It might not be the absolute latest real-time data, but it's often good enough to keep the application functional and the user happy. It acts as a readily available backup data source during outages.
Right, like keeping a copy of the menu handy even if the main ordering system is down. Okay, so we have circuit breakers, retries, fallbacks, timeouts, caching. Quite a set of tools. How do they, work together in a real situation? Can you give us an example?
Absolutely. Let's stick with that online booking system example. You're trying to buy concert tickets, you hit confirm purchase, and the app needs to call an external payment gateway. Let's say that payment gateway suddenly becomes flaky or goes down.
Okay, the dreaded moment. In an old app, I'd probably just see a spinner forever, or maybe a scary server error page.
Right. But in a resilient Spring Boot app, first, the call to the payment service would likely have a timeout. If it doesn't respond within, say, 5 seconds, the app doesn't just wait indefinitely.
Okay, good start.
Now, let's say it times out or it returns an error. The app might be configured to retry once or twice, just in case it was a blip.
Makes sense.
If the retries also fail, Or if the payment service is consistently failing, the circuit breaker monitoring that service will likely open. This immediately stops any further payment attempts from even leaving your application for a short period. It protects your app from getting bogged down.
So it stops hammering the broken service.
Exactly. And because the circuit is open or the retries failed, a fallback mechanism kicks in. This is crucial. Instead of an error, the user might see a message like, "Sorry, we're having temporary trouble processing payments. Your seat selection is safe for 15 minutes. Please try again shortly."
Ah, much better. So my work wasn't lost.
Precisely. And while all this payment drama is happening, maybe the user wants to browse other events or check their account page. Because the system uses caching for things like event listings and user data, those parts of the application likely continue to work perfectly fine, serving data from the cache even if the main database connection was also momentarily slow.
Wow. Okay. So it's this combination, this interplay between the tools that really keeps things afloat. It's not just one thing, it's designing the whole interaction to anticipate failure. That's really insightful. We've talked about the tools and how they work. But let's zoom out again. What are the really gritty, real-world problems that using these resilience patterns actually solves? Especially thinking about someone maybe newer to building complex apps.
Yeah, that's a great question, because these aren't just theoretical concepts. They solve genuine pain points developers face constantly. Probably the biggest one is avoiding those app crashes caused by external failures. Your app often depends on other services, APIs, databases, message queues. If they fail, a non-resilient app often just crashes or throws nasty errors at the user.
Been there.
We all have. But with circuit breakers and fallbacks, your app can intelligently isolate that external failure. It stops sending requests, maybe uses cached data instead, or provides a graceful fallback message. Your app stays up and running even if one of its dependencies is down. Another huge one is tackling slow performance during issues. You know when an app just becomes sluggish and unresponsive? Often it's because it's stuck waiting for a slow downstream service.
Ugh, yes. The infinite spinner.
Exactly. Timeouts are the direct answer here. They put a limit on waiting. Retries can also help if the slowness was just a temporary spike. Together, they keep your application feeling responsive, even if parts of the system it relies on are struggling.
Yeah, a slow app can be just as frustrating as a completely broken one.
Totally. And then there's the really scary one, cascading failures. This is the domino effect. One small component fails, maybe a database connection pool gets exhausted, and it triggers a chain reaction that brings down the entire system.
Like pulling one Jenga block and the whole tower comes down.
Perfect analogy. Circuit breakers act like firewalls here. They contain the fire to the one component that's failing, preventing it from spreading and taking down everything else. Fallbacks provide alternative paths, stopping the ripple effect. You isolate the problem, the rest keeps working. Also, think about high maintenance effort. For developers, especially beginners, constantly fighting fires, restarting services manually, patching things after an outage, it's exhausting and stressful.
Yeah, it burns you out.
It really does. Automating retries and fallbacks handles a lot of the common recoverable errors automatically. It reduces the need for manual intervention, freeing up developers to actually build things, not just fix broken things. And maybe the most important one ultimately is solving poor user experience during failures. Errors, crashes, unresponsiveness, these things kill user satisfaction and trust. Using fallbacks and caching ensures the user almost always gets some kind of useful response. Maybe it's slightly stale data, maybe it's a polite message asking them to try again, but it's infinitely better than a cryptic error code or a blank screen. It keeps users engaged and minimizes frustration.
So it really shifts the application's behavior from just breaking to actively adapting to problems. That's a powerful difference.
Okay, this sounds essential. Now, for our listener who's maybe working with Spring Boot or wants to start, how do they actually do this? How do you enable this stuff? Is it complicated?
That's actually one of the best parts. Spring Boot and related projects make it surprisingly accessible, especially compared to how complex these patterns can be to implement from scratch. The typical first step is simply to add a resilience library to your project. You'd add a dependency in your build file like pom.xml for Maven or build.gradle for Gradle. Libraries like Resilience4j or the older Spring Cloud Netflix Hystrix, though Resilience4j is generally preferred now, are common choices. Spring Cloud Circuit Breaker is another abstraction layer.
So like adding a toolkit to your project. Exactly, you're adding the first aid kit, the tools you'll need. Once the library is there, you can start using its features. To set up circuit breakers, it's often as simple as adding an annotation, like at circuit breaker, to the method in your Java code that calls the external service. Then, in your application configuration file, like application.aml or application.properties, you define the rules for that circuit breaker. How many failures trigger it to open, how long it stays open, things like that. You also specify the name of a fallback method to call when the circuit is open.
Ah, so it's declarative. You're telling Spring Boot what you want, not necessarily coding the how step by step.
Precisely. It's very much in the Spring philosophy. For enabling retries, it's similar. You might use an annotation like @retry on the method. And again, in configuration, you specify how you want it to retry. Maximum number of attempts, maybe how long to wait between attempts, called
Yeah.
a backoff period.
Okay, seems manageable. Timeouts.
Timeouts are often configured either directly on the client making the call, like a REST template or web client in Spring, or sometimes within the resilience library's configuration as well, depending on the specific setup. You're essentially saying, don't wait longer than X milliseconds to this operation, and for stays. Using caching for fallbacks, you typically integrate a caching library for Spring. Spring Boot has excellent auto-configuration support for popular ones like ehcache, Caffeine, or Redis. Then you'd use caching annotations, like @cacheable, on methods that fetch data. Spring handles storing the result and returning the cached version on subsequent calls. Your fallback method might then explicitly try to fetch from the cache if the primary method fails.
That does sound quite integrated and, well, less intimidating than I might have guessed. So why is this approach using libraries, annotations, configurations so great, especially for beginners?
Well, a few reasons. First, it dramatically lowers the barrier to entry. You get sophisticated resilience patterns without having to write and debug complex state machines or threading logic yourself. The libraries handle that heavy lifting. Second, it leads to more reliable applications much faster. You can add significant robustness with relatively few changes to your core business logic. Third, it reduces that manual firefighting we talked about. So much error handling becomes automatic, which is a huge relief and confidence booster when you're deploying your first real apps. And finally, just prepares your applications for the real world. The internet is messy, services fail, networks are unreliable. Building with these patterns from the start makes your app fundamentally better equipped to handle it. Now, having said all that, these tools are powerful, but they aren't magic bullets. It does bring up the question, are there things you need to watch out for? Any common pitfalls?
Ah, good point. What should people keep in mind?
Definitely. One common mistake is setting too many retries. If a service is genuinely down or overloaded, hammering it with constant retries can actually make the problem worse, both for the service and potentially for your own app if those retries consume resources. You need sensible limits, maybe 2 or 3 retries, often with an exponential backoff, waiting longer between each retry.
Right. Don't DDoS your own dependencies. What else?
Fallbacks need to be meaningful. Just returning null or throwing a generic exception isn't usually a great fallback. A good fallback provides useful alternative data, like from a cache, a helpful message guiding the user, or maybe triggers a different workflow. Think about what the user can actually do with a fallback response.
Make the plan B actually useful, not just an error message in disguise.
Exactly. And also be aware that while adding these libraries is easy, configuring them properly does take some thought. You need to tune the thresholds for circuit breakers, the number of retries, the timeout durations based on the specific service you're calling, and your application's needs. The defaults might not always be optimal.
So a little bit of tuning is required.
A little bit, yeah. And related to that, while these tools are great, adding resilience does add some complexity to your system overall. There's configuration to manage, and you need to understand how these components interact. For beginners, my advice is usually to start simple. Maybe add retries to a couple of critical external calls first, then introduce circuit breakers for the most flaky or important dependencies. Don't feel you need to make everything resilient on day one. Build it up incrementally.
Start small. Focus on the critical paths. That sounds like solid advice for pretty much anything in software development. Okay, so let's bring this all together. What does this mean for you, the listener? We've taken this deep dive now into how Spring Boot apps can be built to be really robust, reliable, and user-friendly, even when things go wrong.
Yeah, I think the key takeaway really is that resilience isn't some magic, unattainable goal. By understanding and applying these well-established patterns and tools, things like circuit breakers, retries, fallbacks, timeouts, caching, which Spring Boot makes quite accessible, you can dramatically improve how your application handles the inevitable bumps and failures of the real world. It's about consciously designing for that robustness.
Absolutely. And just to leave you with a final thought, now that you've heard about how software can anticipate failures and build in these backup plans, these plan Bs, Think about that concept more broadly. How could that kind of foresight apply outside of programming, where in a project you're working on, or maybe even just in your daily routine, could a small, seemingly minor fault potentially lead to a bigger cascading failure if you don't have some kind of fallback or circuit breaker in place? Something to chew on.